Yeah, so hello everyone. Thanks for joining the temporal graph reading group today. We are very excited to have Renhe here to present us two papers today. First is the spatial temporal metagraph learning for traffic forecasting, and the second one is the DL-Traff survey and benchmark for deep learning models for urban traffic prediction. And in terms of like Renhe, he is a full-time lecturer at Center for Spatial Information Science, the University of Tokyo. He received his Bachelor of Science in Software Engineering from Dalian University of Technology, China in 2012, and his master degree in Information Science from Nagoya University, Japan in 2015, and his PhD in civil engineering from the University of Tokyo, Japan in 2019. From 2019 to 2022, he was an assistant professor at Information Technology Center, the University of Tokyo. His research interests include data mining and machine learning, especially spatial temporal data science, spatial temporal AI, multivariate time series, urban computing, and intelligent transportation system. So we are very excited to have him today, and I will hand the mic to you, Renhe.
Okay, thank you. Thank you for your kind introduction. Actually, here's my homepage. Basically, the information is listed here and listed here, so you can check this. Actually, I'm a lecturer at the Center for Spatial Information Science, the University of Tokyo. From the name, you can see that it is called Center for Spatial Information Science. Actually, this center is kind of a group of geographic information science professors started this center, and now we are focusing on the spatial temporal data and urban computing and the smart city. And let me start.
If you want, you can share the link to your personal website in the group chat.
Okay.
I will also update it on the website. Yeah.
Okay, thank you. Here, my personal, yeah. And by the way, the lecture, this title is something special for Japan. It is between assistant professor and associate professor. So in Japan, it's first assistant professor, then lecturer, then associate professor, then professor. It has 4 rank. Yeah. And today, I will change the order for your convenience for our audience to get better understanding what we are doing, because I think the temporal graph reading group is we are not so familiar. I think the audience are not so familiar with the traffic prediction. So I think I should start with this CICAM paper. Then I will go back. Then I will go to our this year's III paper. Okay, let me start. This kind of background introduction, so you can just enjoy it. Nothing about a new methodology. Is as this title said, it is a survey and benchmark for deep learning models for urban traffic prediction, and it's published in CICAM 2021, and very lucky, we received the best resource paper runner-up. It is a resource paper, yeah. And this background, our research problem is like this: urban traffic prediction. Actually, here basically this is a benchmark called Metro LA. It's a traffic sensor data set collected from LA highways, highway roads. So each point stands for a sensor. It's just deployed on the traffic roads. So for example, for this picture, we have 207 sensors, and the time range is 4 months, and the frequency is every 5 minutes. So actually, this data is can be modeled as with a 3D tensor. It's TNC. T is the total time steps, and N is the total spatial domain. In this case, is 207. So and the C is the channel, the number of information channel. Here, because the sensor is traffic speed sensor, so the C is equal to 1. But in other case, C can in other application scenario of our problem, urban computing, C can be equal to 2. For example, if this temporal domain, each spatial unit can be a region. The region can record the people flow or taxi flow or sharing back flow, in-out flow, and inflow and outflow. In this scenario, C, the channel, can be equal to 2. Also, for example, if we the spatial unit can be the spatial region. For example, if we record the multiple transportation modes like car and train, subway, and the bus and the walk, so the C can be larger than 2. It's just equal to the number of transportation modes. Okay, so based on such kind of data set, data is a 3D tensor. We want to do the forecasting problem. This is the basic problem setting we are doing now. And actually, there are a lot of studies have been published because we mainly like this field is mainly like applied data science or applied AI. So there are a lot of papers. Even now, this 2023, a lot of papers submitted to top conference or top journal, top venues. And let's say actually this table is summarized. The number, the citation number was collected 2 years ago, maybe I think 2 years ago. Yeah. Currently, for example, there are a lot of SOTAs reached, for example, 2,000 times citation. For example, STGCN and the DCRN. These are two first stated SOTAs published for traffic forecasting based on graph neural networks. And also for the first one is the grid-based model, because for example, for this figure, we can see it is based on it is natural based on modeled based on the road network. It is a graph. But if we just grade or mesh the entire urban area into into multiple mesh grids, so it can also our problem or the traffic prediction problem can also be built based on the mesh grid. So, for example, this ST-ResNet, Spatio-Temporal ResNet, reached also almost 200 times citations, I think, by now. So, what I want to show is that this field actually, this Spatio-Temporal data modeling field, or also the urban computing field, and actually are drawing lots of attentions. And the prediction tasks, you can see that it is something taxi inflow, outflow, or taxi demand, or some traffic volume or traffic speed. So although these prediction tasks may kind of different from each other, but actually the models can be applied to one another. It's all common techniques. And the metric is RMC or MAE, because these are typical regression problems. And so why we want to do some studies, do a survey and benchmark or a resource paper, because like I said, although the tasks may slightly different with each other, but they can also they are all can be formulated in a uniform way as this, given past alpha steps observations, and then predict the future beta steps. And for each step, actually, this is the whole snapshot for the entire area. It is n multiplied c. Usually, c can be like I introduced, c can equal to 1 or multiple. N is the total spatial units. It can be nodes, graph nodes, or the number of the grids. If you get this, I think the problem setting you can just understand or take it very easily. So with this benchmark or this this repository DL-Traff, so you can first grasp the technical details about the spatial temporal models, and then you can reproduce them, the baselines or the SOTAs. Also, you can, based on, because we have two versions of this, one is TensorFlow, another is PyTorch, you can also develop your own models. And also the dataset, we also do a summary of the benchmarks. Is Taxi Beijing and the Taxi NYC and New York City, and the bike sharing back New York City. Like this, for example, the city bike. This link here shows that this dataset is totally open, and it is kept updating every month, I think. Also, for this New York taxi dataset, is also totally open, and you can set your own spatial domain and make your own mesh grid size. Then you can do you can create your own dataset. However, most of the dataset, for example, follow the previous literatures, and they just use this specification settings, and then a lot of studies follow this. But anyway, I want to say that the original, really the data source, from the beginning is from totally open dataset, and you have to aggregate them by your own. Yeah, and then another another string or another track is graph-based. It is like I just showed in the first page. It is from collected from traffic sensor. Also, traffic sensor is LA and California. Like this is a PEMS. A lot of data sets are collected from a PEMS system. Yeah, and the most famous two are like this: Metro area and the PEMS Bay. These are their specifications or settings. Yeah, and we aggregate all this Taxi Beijing back NYC, Taxi NYC, Metro area, PEMS Bay, and the PEMS D7 are integrated into our benchmark. And so we also do some surveys on the models. And here I want to tell you that the challenges for our spatial temporal data modeling tasks is to deal with complex spatial and temporal dependencies simultaneously. For example, temporally, because it is basically a time series problem, so past future prediction of future values naturally depends on the past. No matter it can have some periodical or some or something. So not only the literally the recent alpha steps, but also can be also past 1 week, several weeks, or several months. So like this, and especially you may all familiar with GCN, the concept of GCN, the one node or one region naturally will affected by the its neighbors, as well as some distant ones. For example, in this city case or this spatial area case, one region actually, for example, if we observe this for 1 hour, this CBD region or this downtown area, the traffic of this for this downtown area can be actually affected by a very suburban area. It's something like this. So here, for example, if we model it with a mesh grid, it is a Euclidean space, so we can use a normal CNN like an image. But if we model it with a graph or with neural networks, we have to use graph neural networks. Yeah. So basically, we decompose all the model all of these models into two axes. One is spatial axis and the temporal axis, And the spatial axis, for example, they use CN or GCN or attention, and temporal, they use RSTM, GRU, TCN. This is a temporal convolution neural network, and also attention transformer. So like this, we decompose the basic technologies they use in their model into this table. So we also conduct some surveys, at least a very highlight view for this various sort of models. And for example, this figure 3 in our original paper are the representative architectures for grid-based models, because these grid-based models, and also we pick up very representative models for graph-based GCN-based models like this, including STGCN, DCRN, and GraphNet, and ASTGCN, and GMAT, and this. And if you also in our paper, we briefly introduced how these models evolve along both axes. One is temporal axis, and another is spatial axis. How they gradually become stronger and stronger. Yeah, you can check the paper. And at last, we do some benchmarking and based on the open data set. So this is a very simple benchmark. Also, not only the effectiveness, but also the efficiencies. And we do such kind of thing in our benchmark. Yeah. So here is a kind of basic instructions for how to use our project or this benchmarks. Yeah. Anyway, this also was written in our README in the repository of our project. So yeah, if you have interest, you can kindly have a look on that. Okay, that is all. I think this is a kind of a long version for today's background introduction, and then we can move to our recently research achievements. It is called Spatio-Temporal Meta Graph Learning for Traffic Forecasting. Even though the title explicitly includes the term of traffic forecasting, but we believe that our model actually can be applied to many multivariate time series datasets. But unfortunately, if we want to claim that we can apply to a lot of multivariate datasets, we have to do a lot of experiments. So in this paper, we only focusing on traffic forecasting, and also you can see this collaboration research or project with Toyota, Japan's largest, maybe the world's one of the world's largest automobile company. Mobile company. So we not only use a benchmark traffic benchmark, but we also collaborate with Toyota to publish a new dataset I will introduce later. Okay, so here I think we can just skip this because this is just the background I introduced in last part, in the previous part. Anyway, it is given past alpha steps, the whole snapshot, the graph snapshot to predict the future beta steps. Yeah, this is kind of different. This is actually the key difference with for example, TGN problem setting, because TGN we basically give start node and end node and the timestamp and the edge information, and to predict the future, to predict in the future within a time window if these two nodes will have some interactions or will have some edges. It's kind of node level prediction, but in our case, this because we want to focus on the whole urban area or the spatial area. So this is a whole graph level prediction. You can know that, and except the spatial temporal dependencies, we have to our model. This actually all the previous models have to deal with the spatial dependency and the temporal dependency simultaneously. This is all basically the fundamental challenges in this multivariate time series forecasting, as well as this the representative sub problem, which is the traffic forecasting. But also in this paper, we kind of propose or focusing on these two challenges in traffic forecasting. And based on this, actually, these are also our motivations to propose our methodologies. One is heterogeneity, because you can see that the traffic condition differs over roads and time. Okay, for example, if it is a highway, the average speed can be very high. Look at this y-axis. Actually, because it is highway, the speed is high. If it interchange, driver must stop to pay some ETC fees or something like that. So the average speed can be relatively low. Actually, here the heterogeneity just says different nodes may share some nodes may share some common patterns, and another group of nodes may share some features, some common features patterns. Also, during, for example, this rush hour, morning rush hour and the evening rush hour can somehow share some common patterns. But for example, during daytime, can share another type of patterns. It is the idea of heterogeneity. It actually here also can corresponds to spatial and temporal heterogeneity. Okay, and then it's non-stationary. Non-stationary here we actually in this paper we focusing on the traffic accident scenario. For example, suddenly because of a traffic accident, the traffic congestion will happen. Then the traffic speed can suddenly drop down like this. So how to effectively solve this two problems besides the spatial temporal modeling is what we are focusing in this paper. And this paper, we like the title said, the graph learning. So we kind of follow the research line of graph learning, because for this traffic forecasting, we have a lot of research lines, and some are, for example, based on transformers, and but there are a lot. We're particularly interested in graph learning, because this is a typical road network is a typical graph structure. So we want to use to improve the GCN-based methods to another level, and with better interpretability, and better can solve this two challenges. So the typical.
Sorry to interrupt. Oh,
yeah.
Sorry. There are two questions from the audience, so I thought maybe it's good to answer it now before moving too much into the second paper.
Okay.
So I can read it out from the chat, or like you can unmute yourself.
Okay. First, can you provide some more detail about complexity analysis of our models? Okay. Sure. Actually, this is a very good suggestion. We kind of not explicitly give this complexity analysis, and we can try to put on our repositories, because this is not difficult. We can do that. Yeah. And the second question is, in the page listing why the grid-based ones had the. Okay, that's a good problem. Yeah, a very interesting find by you, and yeah, you are right. You are right. Because you can see that the if the grid-based ones, I want to say that it's more like transportation demand, not it is actually based on the traffic, but not based on the traffic sensor data. It's based on, for example, taxi data or bike data. So if for example, this data set actually a more how to say more illustrative way to think about this data set. You can think about it. You can take it as, for example, there is a Uber data set or Didi data set, Didi and Uber. So actually, this companies care about this problem. So this is a transportation demand problem. So every 5 minutes, we don't they don't usually care what happened or forecasting what 5 minutes later will be. So this is in this problem setting, maybe a little bit longer time interval is more meaningful for this case. And for this case, the below one is graph-based. This data sets are all from traffic sensors. And so the traffic sensors, this is recorded the traffic speed. So this is in this problem setting, and usually we use 5 minutes. But you can also see some, because this is data set all from very the very original data sets from this system, PEMS system, can be very fine-grained. Also, for example, you can do it, you can aggregate by yourself. Also, for example, this data set, the traffic data set, this is also several sort of papers use this data set, but they just aggregate into 1 hour. So they just think 1 hour prediction is enough. So it's kind of tradition. That's what I want to say. I hope this can be a satisfied answer. If so, we can continue. Can we continue? Okay, thank you. Okay, cool. Let's continue. Okay, let's go back to graph structure learning. Previously, we all know that the GCN relies on a predefined graph structure. For example, in our case, it's usually distance or adjacency matrix for among the row networks among different rows. And gradually, we can briefly introduce the progress for this graph structure learning in this traffic prediction field. First, because this predefined one is predefined, so it doesn't change. So it's don't have a very good adaptability. So first, they use the they give parameters for each node. This is a learnable parameters for each node, the node embedding, and then use is the multiply the node embedding and its transpose to get a learnable graph. It's like this, okay? And then gradually we have this kind of dynamic graph learning. We call it momentary graph learning. It's like this. For given this is you can say this is actually conditional on the input. Given different input, we have a learnable parameter, and then based on the different input, we can generate a dynamic graph. This is the first compare with the first one. This is more momentary or more dynamic. But also we think we can do a better job. We want to do propose a better spatial-temporal graph like this. First, we introduced this methodology. the backbone. You may not so familiar with that because but this actually quite widely used one in our field. It's called graph convolutional recurrent neural network. It is basically we embed. You can see this formulation. We embed the graph convolution into the GRU module, and to replace the full connection in the original in the vanilla GRU to get this, and then use this basic backbone. We can do the spatial and temporal modeling simultaneously, and also for this GCN part, we use this formulation. This is a very traditional one, and for this graph learning, we just use the first one, the adaptive graph learning, like this. This is the backbone. This encoder and decoder. This alpha step and beta step. And go back to what we propose is called a metagraph. Actually, this is kind of motivated by the TGN temporal graph network. We propose a meta node bank. This node bank, this is actually a memory network. We use this memory network to store the current hidden representations learned from the current input dataset, and then we set several meta nodes. In our case, we use 10. That is to say, we group and or clustering all the spatial temporal patterns into these 10 patterns. Actually, this meta nodes actually store the spatial temporal patterns, not only the spatial patterns, like this. So you can see this H is this H is this H is latent representation. The spatial temporal latent representation learned from the input data set. This X actually the total alpha steps X contains all the spatial and the temporal information, like this. And this is purely attention-based module, and this is a query, and then we get the average. We get the query result. You can see this as the queried value. Yeah, like this. And based on this, after this, this memory network or the meta node bank will be updated. Then based on this updated memory node bank, we generated this graph, this adaptive graph. So through this part, I think we can get the heterogeneity and the non-stationary, because this can this meta node bank first can store the patterns, then it can store the kind of has the ability to discriminate what are the normal patterns and the abnormal patterns. So it has the two functions. And so let's put them together. It's like this. This is not our contribution within the GRU gray frame. So this part, the below part, are our contributions. And first, let's go through this workflow. First, if we get given input, we have an encoder, and then the encoder have a HT, and this HT is the spatial temporal hidden representation, and then go through a query, then query the meta node bank to find is the most similar one, and the second most similar one. It's like this. Yeah. Actually, after this query, we get three tensors. One is this is after sparse attention. It is a kind of averaged one. It is called M, and another is, I said, the most similar one, and the second most. And because after getting this we take the most similar one as the positive sample, and the second similar one as the negative sample, and we put the contrastive learning loss into this final our target, and to better to learn a better meta-node bank like this. And then this is if we conditional on this dynamic meta-node bank to generate a graph. This is E is just the node embedding for each node, and we use this formula. This formula to get the graph. E multiply is transpose. Basically, it's like this. So the key idea is this meta-node bank, and a trick we are very proud of is this contrastive learning. This can help the meta-node bank better learn. Yeah. So here are our experiments. We have two traffic benchmarks. This metro area and the PMSB already introduced in our benchmark papers. Actually, a lot of papers use this too. And the visualizations are like this. And this one, EXPY, TKY is short for Tokyo, and EXPY is short for expressway. Actually, you can see that the spatial unit is almost 6 times larger than the previous benchmarks. And yeah, so this is a more larger scale data set. And actually, it covers all the expressway highway roads within the core Tokyo area, like this. It's almost 200 road links like this. So we pick up 8 samples from this 8 spots, and to give a time series visualizations. And here is a video to show the original dataset. We collaborate with Toyota. Yeah, actually, this is the original GPS trajectory dataset collected from Toyota connected car. Yeah. Then this is GPS dataset. We do some aggregation and to get this dataset. Okay. Because the origin also there are some preprocessing. You have to align each point with the road network. It's already done by Toyota, so you can see that each actually is pretty clear. The whole road network. Okay, our baseline is like this. The fully convolutional solutions, STGCN, graph ViewNet, and the MTGN already introduced in our previous benchmark papers. And also we included 2 transformer-based ones, and also some GCRN-based GCRN-based models like this. Especially this backbone are like this. Also, we because there are a lot of baselines, we cannot compare them all. But we compared with various representative graph structure learning models. First is there are 4 models can be categorized to. The first one is called adaptive graph structure learning. It is graph ViewNet and MTGN and the CCRN and the GTS. This is graph structure learning. And also another one is momentary. Actually, there are not so many models, because as you see that I want to state again that because as you see that this is conditional on X. The input, the graph is conditional on each input X. So this cause the graph learning is very difficult learn such a momentum graph. Although this paper, yeah, so it is very, very difficult to train. So only I think this paper success, but this paper has some problem of reproducing. So I gave a note mark, and this because it is not so difficult to reproduce that good performance. And after this, this is the performance on our data. And this is performance on the two benchmarks. And yeah, we all reached the new result levels. And also, these are some ablation studies. You can see if we use GCRN, because our model is the backbone is GCRN, we only use adaptive graph. It is the first one. And if we only use adaptive graph and the memory network, which means we don't we have the memory notebook because we can get augmented hidden representation HM. But we don't use a hyper network to dynamic generated the graph from meta notebook. We only use a memory network to get augmented M like this way. So then this is the second application, and the third application is a momentum graph. We don't use meta notebook. We just conditional on X. It's like this. The results are like this. This meta graph way is a better way, and the efficiency study is like this. I will skip, and I will show some visualization of case studies. First, it is called spatial-temporal heterogeneity. You can see that this is the TSNE visualizations. If we only use the GCRN plus adaptive learning, so the result will be the first one. There are no clusters, so the patterns, there are no clear patterns learned from the graph structure learning module. But if we use our metagraph learning, and we can see that there are clear two patterns. First is, for example, the red one and the blue one. After checking our dataset, because we can our dataset can mapped can be visualized on map, and we can check them very in a very fine-grained way. We can see that the blue link actually in this cluster, within this cluster, the patterns are all like this, and the red link are like this. We found that cluster 1 actually corresponds to the highway road links, and cluster 2 corresponds to interchange road links. And so the cluster 2 average speed is much lower than the first than group 1. Also, if we look at the subgraph B and C together, we can see that during each step, the clusters or the shape of this patterns change, but still they can be two different clusters. So this verifies the spatial and the temporal heterogeneity. Yeah, and the second is the non-stationary scenarios. We can see that our model actually because it can somehow handle the sudden change cases better than the baselines. And after checking the memory query weights, because we can just visualize the memory query weights, we can see that our memory query mechanism actually works. Also, we can see that it plays an important role in capture such non-stationary scenarios, because you can see here. Here, the query weights actually, if nothing happens, it's like this. But if something happen, some weights can be changed, can contribute to such sudden change scenarios like this. And we also visualize subgraph. If we can see that if at 2150 there is a traffic accident at node 1. Before this traffic accident happened, the subgraph is like this. The bigger nodes, the size denotes the size of this nodes the importance within this dataset, within this subgraph. So because this is an intersection, this node 1 plays a very important role if nothing happens. But when the traffic happen here, so this kind of the congestion, so the node 1 is no longer the most important node within this maybe 11 nodes subgraph. Yeah. So this is we verified the impact of the accident with this subgraph. Okay. Through these two case studies, we verified our proposed methodologies actually can handle this our two challenges very well. Okay, the dataset and the code are published here. Especially, I encourage you to use our new dataset because this is a very larger one, and we also provided the graph or the adjacency matrix. Also, we have the roads. Each road links coordinates, the longitude and the latitude. This supporting informations are much better than the previous one. Not only the scale. Yeah. Okay. Thank you so much. That's all for my today's presentation.
Yeah. Perfect. Thanks so much. Yeah. Thanks for going over both the background and the and your very interesting paper. It sounds really good. And so the code are like also very reproducible. Do we have a question from the audience? I think we have a question from the audience, so maybe we can do that first.
Okay. This file. Okay. I see. Thank you. This file is actually kind of redundant. 5 plus and 5 plus p means the how to say that after each because this is this cube inside each cube there's a small small rectangular cube means each node is for this is sorry I will show with this. This is for each node. This is actually represents each node's hidden representation, and so for each node we can through this memory meta node bank to get its most similar one, the most similar one as is positive samples, and the second most similar one as is the negative samples. So this p and plus this p I want to show is the indexing function, and this n is the indexing. We find the most the index for the most similar one and the second most similar. Yeah, this basically the contrastive learning, and this m is the aggregated one through this sparse attention. Yeah, this is actually the queried values. Yeah, the values after query. Yeah. How? Okay. Let me answer. Hope this 5 problem has been solved. Okay. I will move to the next question. Okay. Thanks. I wonder if you have a chance to test your approach on. Yeah. Thank you. Actually, we tested on because our dataset actually does not our model does not relies on the predefined graph structures. That is actually exactly what we want to solve. So our methodology can be applied to any other multivariate time series forecasting problems or datasets. For example, this nodes actually each node can be seen as a variate, and for example, this can be multivariate time series. For each node, we have a time series, and I have applied this methodology to electricity dataset, and electricity dataset we found that it can it has some limitations actually. The limitation is like this. It goes well for the first few steps, but for the longest horizon, it failed. It cannot be better than the baselines because the time interval for electricity dataset is 1 hour. It's a bit longer. So this GCRU or the recurrent neural network backbone has no advantage for that kind of long sequence forecasting problem. So in that case, we may consider to change our backbone, for example, to transformer or temporal convolution neural networks. Yeah, actually we are doing that. Apply our model or verify our model to a more temporal or more multivariate time series forecasting problem. Yeah. Okay, I will go to the second another. This to illustrate with TSE means your model has to predict in the interchange heterogeneity. Is this right? The interchange and the heterogeneity. Almost that. But I want to say that first, we have this TSNE, right? And then actually after you apply TSNE, you don't have the color, and but it has 2 clusters. And then to better realize or illustrate this cluster, this effect, because these 2 clusters are naturally automatically learned from this data set. So after this coloring, we further check the nodes within these clusters with this map visualizations. For example, this node corresponds to this road. Then we from this we get this, and then we check the patterns. Then we found that because we can further zoom out, I think, zoom in this map, we can find that cluster 1, the neural networks, the links within cluster 1 are mostly are all highway road links, and the cluster 2 within this within the road links within cluster 2 are most interchange road links. So this verifies this heterogeneity. Our model can automatically learn this this patterns. Yeah, this is how to understand that. Okay. Maybe the last question is how our meta node bank update. Okay. At the first because first we have to use this basic GCRU module to get a hidden representation like this, and the hidden representation will pass to this meta node bank. This is actually a query, and this is actually this is a query to query meta node bank. And then how to update it is I think the key to update this meta node bank is contrastive learning. If we don't apply this contrastive learning, maybe the cluster, we cannot get the cluster automatically. Yeah, and for each time after query, we get this hidden augmented hidden representations like normal like the sparse attention mechanism, but also we get the positive sample and the negative sample, and then the objective function is like this. This is this left this part is the MAE loss. This is MAE R1 regression loss, and this two parts actually this is we called it a compact loss. You can see that we use a positive. This is a positive one. We want this query can be as close as the positive ones, so it's kind of a cluster effect. And then another is contrastive learning. We call it a separate loss. We push the different clusters as far as each other. We combine these two to this our objective function and to update it. Yeah. Okay. Hope. Okay. Thanks.
Yeah, thanks for all the excellent questions, and thanks for answering all the questions, Renhe, and thanks for the presentation again. So
okay.
Yeah, so let's thank Renhe for the presentation again, and we're at the end of the hour here. So so we'll all see you like next week at the reading group as well, and have a nice week and weekend, everyone.
Okay, thank you.
See you next week.
Yeah, thank you, Andy. Thank you, Andy,
Bye.
for giving me this opportunity.
You.